Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from HP. We have John Gromala. He is a Senior Director of Hyperscale and Product Management for HP servers. John, welcome to the show today.
Thank you very much. Glad to participate here.
Well, thanks for coming on, John. I imagine you had a very busy week at HP Discover and rolling out these new Apollo server family. How did it go for you?
You know, it was actually a wonderful, very successful week. We were actually the talk of the show. You know, a lot of great focus on not only these new platforms, but even more so how the opportunity in high-performance computing is growing beyond its sort of traditional roots to be something more pervasive in the industry.
Yeah, and as a longtime HPCer, I was really happy to see Apollo come back as a brand in HPC. Long legacy there.
Well, you know, ultimately we wanted to talk about these as a new platform, new capabilities. There is some legacy within HP of having those platforms, and it's something great that we like to be able to tap into. The legacy of even 75th anniversary of HP overall. This is also our 25th anniversary of our x86 server line, the ProLiant line. So lots of rich legacy like Apollo for us to tap into.
Well, great. Well, why don't we jump into it here, John? I brought your slides up. Why don't you go through that, and then we'll do a Q&A at the end.
Sure. Just a quick overview of all the different things that we're looking at and capabilities of these new HP Apollo systems. First, as I mentioned earlier, we really see high-performance computing expanding in its traditional area of government and academia, but going beyond that as well. We've got that larger focus in government and academia, but now it's becoming a ever-increasing tool even in the world of enterprises. As you'll see here, we've got all these bigger problems that we have to solve out in the industry. And, having the right tools to do that becomes more important than ever. It used to be a case where a lot of the world of engineering and technical took place primarily in labs and people would do measurements and all. That physical world of doing things is still present, but it's a much smaller part. People are now moving more of that to the digital or virtual world where it's a world of doing designs electronically and doing simulations electronically to better understand how things work and go together. And then it's just a final validation back in the physical world. So it's a great case where all of those pieces are starting to be more pervasive, not only in some of those great scientific areas that we all know of in government, academia, and R&D and life sciences, those traditional HPC areas, but it's even now the case where a lot of automakers, airline manufacturers do their entire designs digitally so that they can go ahead and simulate the results and then take those simulations and better update those digital designs. Because of that pervasiveness, we really are looking to create new platforms from HP where we need to balance three major things across our line, and each of our products will have a different mix of each of these things, but there's no question performance is about all that we do, but it's performance with that balance of efficiency that makes it practical to be used pervasively. We want to be able to use these more broadly, and how do we come up with a platform that gets you that high performance that you need with an efficiency that makes it so that you can operate that and use it more broadly. Then ultimately, it's about accessibility. This is an important tool that people are using across the board, and we want to make it something that a lot of different folks, even as you'll see in some examples later, down to some small and medium businesses want to use. When we look at HPC, we think it's a case where this is the key piece that's going to define our tomorrow. And I know that's a big statement. How we look at climate modeling, how we look at increased safety in automobiles, how we drive a lot of these more challenging questions and scientific and technical problems that need to be solved. that most important tool is HPC. And we at HP wanted to challenge ourselves to create a new set of tools for the world of high-performance computing to make HPC more broadly available, and also provide new ways for us to get even the highest performance systems out there. And that's a key to what we really are looking at in this new HP Apollo family. I'll go through two of those platforms here today. We'll start with actually the HP Apollo 6000 system. All right, just a quick view at the Apollo 6000. This is really that platform that we want to be available for the broad set of folks, for the masses in deploying high-performance computing. We did take a unique approach for this platform, and it is designed at rack scale. You know a lot of servers where they're single servers, rack servers that are deployed, where you optimize that one rack to do something very well, and then you stack those up in a rack and put power cords to each and every one of them. Instead of that kind of an approach, or a blades approach where I put everything in one enclosure, we wanted to go that next step in hyperscale techniques to really design a system from the grounds up to run at rack scale. So there are chassis that you'll see here in the system that we stack up with networking that is all done at the rack level, and even the power is done at rack level. And what that does is, when we pull all of that together, it allows us to get better performance per dollar per watt. This is sort of summing all of those major TCO pieces, the life cycle operations, all together into one big improvement area, and we can get that 4x improvement compared to any other system out there. The particular case we're talking about here right now is an electronic design automation case. Although the HP Apollo 6000 is a new platform, the first of those servers that we have available on that platform is actually a dual one-socket server. This is a one-piece server where I put two of those servers on each of those trays that I plug into the chassis. To get a large number, you'll see 160 in this 48U rack, 160 of those servers inside that system running at the fastest clock speed I can run those processors. And if why would I want to do that, you might ask? And it's really because these applications that we have listed, the EDA applications, the Monte Carlo-like applications, they want that, very simple, very fast approach in terms of how they're running things. It's a single-threaded type of applications, and how can I run those things fast, fast, fast? And that's how we've optimized this initial offering for the Apollo 6000. Let me go through a quick look at how the different pieces are there on the Apollo 6000 and help explain our approach even more. Next slide, please. So the overall system that we've got, as I mentioned earlier, is a rack scale design. That chassis, as you'll see in the center picture, is 5U high. I can get 10 server trays, and I have 2 nodes or 2 servers per tray based on this first available server tray that we have shipping itself. Great performance in terms of 2 separate processors with up to 32 gig of memory running the latest generation Haswell processor. That's an E3 single socket processor, but it can run fast, fast, fast. It can get 4 gigahertz of performance. Just a great case where you can go ahead and run those single-threaded or lightly threaded applications very efficiently. But again, getting back to efficiency, we not only wanted to have the fastest performance, but by managing the power and cooling at rack scale, we can get more flexibility in how you want to configure it, and you choose whether you want high redundancy, even N+N redundancy, or whether you just want to get the lowest amount of power utilization in the system. So all great cases where we can take advantage of all of those different capabilities and configure the system at rack scale. Final note here before we move on. This 2x1P is our first available server. We are going to have dual socket servers that are available. The next generation of Intel E5 Xeon processors will be available inside the system along with GPU type options, but those will be coming at a later date. Again, our first available system here is a great solution for electronic design automation. All right, finally, let's take a look at, next slide please, the comparisons of what I'm getting inside this new type of system. We took a set of Dell blade servers, and actually it's a common configuration that was used in a lot of these customers with electronic design automation. And did a compare where we could see the difference in performance by having a system that's optimized for that workload. I can get 20% more performance, do it in a significant improvement in rack space, but lastly and most importantly, I can do it with 46% less power. Now on the left, I've got what is the predominantly available Dell blade here, a 2-socket blade that I'm only really taking advantage of one of those sockets because EDA really isn't something that needs all of that extra capacity and bandwidth that blade servers have. By having that more efficient design, I can run those better and having a significant improvement. That's $1 million per year. This is a 3-year TCO compare, a savings in terms of how I operate that system. Very simply, when I look at how much the system costs, it can pay for itself in a very, very short period of time, solely based on that savings. So this is our compare. This is our look at things. We actually had a co-design partner when we pulled together the Apollo 6000. We actually took one of the leading EDA customers out there in the world. Next slide, please. Intel, and actually they worked with us on helping to help optimize this design and system. And in their environment, they're actually getting a 35% performance increase in their EDA environment based on the Apollo 6000. Intel has already shipped and deployed tens of thousands of these systems. So a great case where a real-world set of systems are out there running. We are now making those available more broadly into the industry. All right, that's our Apollo 6000. Now let's transition over to a real exciting piece, HP moving into the world of supercomputing with our new HP Apollo 8000 system. Next slide, please. So we took a look at how the world of supercomputing was taking place. You know, HP is a leader in high-performance computing overall. From a volume point of view, we do good, you know, from an overall top performance kind of end, but wanted to do better and really target a platform specifically at supercomputing. To do that, we wanted to provide the best performance density, the best teraflops per square foot of any system out there. And you'll see we've used water cooling, warm water cooling, to help enable that. When we partnered with another one of those lighthouse design customers, the National Renewable Energy Labs, to do a system that would be targeted at high performance, but doing high performance in a very efficient way, we came to the conclusion that liquid cooling was so much more efficient, actually 1,000 times more efficient than air, that we needed to take advantage of that to get the performance density that we wanted for this high-performance computing area. And we actually delivered exactly on that. We've got, compared to an air-cooled system, quadruple, 4 times the number of teraflops per square foot. We can get over 200 teraflops per rack in terms of our capacity. Obviously, a lot of these systems are deployed with more than one rack. You know, the performance scales from that point on. And we make sure that we do that in an efficient way that can cool things, but also in a way where we're delivering that capability without a lot of the risks of water cooling. And we'll talk about that technology here in a second. But again, getting 40% more performance per watt than air-cooled systems is key to things. We do that through a technology that I'll describe in a minute called dry disconnect, where HP never actually mixes the water cooling portion with the electronics. We use a unique dry disconnect technology to go ahead and move the heat to an area where we do the water cooling in a very, very efficient way. The last and ultimately what may be the longer term most important piece of this announcement is being able to do all of this great supercomputing, but really dealing with energy reuse, energy offset by recycling or reusing the warm water that is generated by the Apollo 8000. We can offset a large amount of CO2 and really make it so people don't need to use a lot of energy to do things like heat their buildings. And we've got one case with the National Renewable Energy Labs. They're using it to keep sidewalks warm so they don't have to do de-icing of sidewalks. Great case where a lot of this can be done much more effectively with a new approach with the HP Apollo 8000 system. So let's take a look at some of the technology that really is behind the HP Apollo 8000 that helped enable that. Next slide, please. All right, we needed to innovate not only at the server level, and we'll talk about that in a second, but also at the infrastructure level on how we would manage that. It really starts with dry disconnect, and we'll do a specific look at that in a second, where we actually get 100% water-cooled components, but do it in a safe way for how I can service and how I can actually operate the systems. It's built on warm water, as we talked about earlier, but our key in terms of how we manage the coolant within the system is our intelligent coolant distribution unit. The ICDU actually can have the capacity to run up to 4 racks. That's 80 kilowatts per rack. Assumed if you're using less kilowatts, you'll be able to do more with those CDUs if needed. But the intelligent cooling distribution unit not only provides that water cooling down that center of the racks, as you'll see in the picture, it also does it in an extremely safe way. We use negative pressure. We use a vacuum in terms of how we circulate the water within the CDU. And we do that because doing that is a lot safer than using positive pressure. If we use positive pressure and any leak did occur, we would be spraying water out within the system, which is a horrible thing to happen for a computer in this case. By using a vacuum, we actually pull air into the cooling distribution system, and very safely we can sense that air is inside the system and know that a leak has occurred in a particular area, and we can have a rack per se actually shut down that one rack, still keeping the rest online, and still manage that system in terms of how we in turn can more safely and efficiently run the coolant with those systems. Lastly, it's all of the ILO management infrastructure that people know and love in the Proliant world, plus additional rack level power management. In many senses, think of the sea of sensors technology that people have grown accustomed to in the world of Proliant. We now can do sea of sensors at a full infrastructure level to know everything that's taking place within that infrastructure and manage it more effectively. Next slide, please. We'll go ahead and do a quick look at dry disconnect. This is the piece that makes it where we can uniquely do the cooling inside the systems without having to actually bring water itself into the server. You'll see we have sealed heat pipes that actually move the heat from the processors and from the graphics processors, the GPUs, to the side of the server. You'll see that line called a thermal bus bar. We then in turn move that heat off to our water cooling area, which runs down the center of the rack. At no point is the water itself mixed on the point where the servers are operating. Heat pipes are a great technology that has been out there for many years. It's pervasively used on a much smaller scale in a lot of laptop computers to move heat from the processor out to an area where a fan can cool things. They're very efficient and use, a little technical here, they use the phase change in the glycol liquid that is actually in the heat pipes to go ahead and move the heat from one area of that heat pipe to another area. So very efficient, very proven technology. There are no moving parts. There are no fans that are required in that system. in terms of its ability to go ahead and do that cooling and operate that system. So lots of improvements in efficiency, lots of improvements in reliability without any moving parts. And then finally, you get that benefit of ease of serviceability, because I can now service that piece without having to do any connection or disconnection of water. I've got a much more efficient and safer way to run water cooling. As we talked about, we designed this system with failure not being an option. Everything from the way we do the connections of the servers to the way we manage the water IT loops, as I mentioned earlier, running them under vacuum, and even, as you'll see in the picture on the right, the simplicity of how we connect up the plumbing is all done to go ahead and optimize how that warm water system is deployed more easily than ever. Looking at how it all comes together on the next page, very simply doing an air-cooled compare to our liquid-cooled system, huge improvements in teraflops per square foot, all coming down to $1 million per year in savings. Not only looking at our compare, on the next page you'll see the benefits that the National Renewable Energy Labs found with our initial system that we deployed with them. Back in November, we brought online the first of these platforms called Project Peregrine. That's the name of the National Renewable Energy Labs project associated with this. It's in deployment, doing great, running very well. They've been getting a PUE of 1.06, which is a phenomenal efficiency, and getting $1 million in energy savings per year just based on this. They in turn are, as you'll see on the next slide, offsetting a lot of their carbon emissions, and reusing that heat provides a lot of huge benefits to them overall in terms of just not needing to use energy in their facilities. All right, services on our next page gives us a quick idea of how we can help customers not only prepare for deploying these systems. If they need, we can help with implementation and support. And as always, HP Services is there as a leading provider of different ways for people to finance these new services that they deploy within their businesses. We talked about earlier on accessibility of those systems. On our next page, you'll see that we have additional HPC as a server offerings within our HP Helion cloud that is available. These will leverage a lot of our Apollo 6000 capabilities, as well as some of our other HP server technologies, to make a service available for HPC. So if a smaller business needs access to HPC, they can get it in this fashion by purchasing those capabilities. And in addition, we've also worked with a lot of academic vendors and Intel to provide HPC resources on a more regional basis. Think of some regional universities making some of their high-performance computing services available as well on a regular basis. All right, so that's a quick overview of all the different capabilities, how HP has not only delivered new capabilities in HPC, we've got that great performance we're delivering with the HP Apollo 8000. We've expanded the platform availability with the HP Apollo 6000 to have a rack scale optimized system that has very efficient deployment of systems. And then finally, new innovative ways to provide broader accessibility for HPC overall. And last slide here, HP, we really feel and take it personal that we want to do everything we can to make it matter for the world of high-performance computing. So with that, any questions?
Well, thanks for that, John. Yeah, a couple questions. I wanted to ask about that big petascale deployment at NREL, the National Renewable Energy Lab. How close is that system to what you guys, turned around and turned into a product, like a year later?
Yeah. So first, there are two major differences. First, it is actually developed on the Intel Ivy Bridge generation of processors. In the Reliant world, that would be the ProLine Generation 8 set of systems. The new one that we're announcing with the Apollo 8000 will actually be a next generation Xeon E5 deployment, so that next generation after that, the Haswell generation. So that's one of the major differences. Aside from that, there's some additional networking capability that we're putting inside the systems as well to get better connectivity of InfiniBand within those racks. When you get this kind of a density of overall computing, you need to pay attention to all of the details, not only of how we cool the system, but because we've got double the density of servers inside that rack, 144 servers per rack, managing the cabling of InfiniBand and integrating that becomes as important a piece of the overall solution as anything else.
Yeah, yeah. And I wanted to ask you, John, about the density. I mean, being able to do 250 teraflops in a single rack, so we're looking at a petaflop scale system in just 4 racks. That seems to me a lot of hardware in a very small space. What about floor loading? You know, you're running fluids through there. That's got to be heavy.
Yeah, so we do have details, and for anyone who's interested, we do have our quick specs or our data sheets on this all available. So it's roughly 4,000 pounds per rack. So yes, people need to make sure that they've got the right floors in place, but it's not uncommon for any type of water cooling systems to need that. So compared to a lot of the supercomputers that people are used to, we're within that realm itself. The biggest area we've seen a lot of people more want to focus on is the power in as well. So yes, weight planning is something that needs to be done, but also, getting 80 kilowatts of power into the rack is just as important as the heat removal that we take place with the water cooling. So lots of important pieces to get worked out, but the benefits of doing that allow people to get that larger scale system.
Yeah, yeah, John, I wanted to put that in perspective. I mean, up to 80 kilowatts per rack. That's probably twice what you could probably accommodate with air cooling, isn't it?
Yes, that's why, and we really see the Apollo 6000 and the Apollo 8000 as complementary products for that reason, that, the 6000 can get you up to, that roughly 20 to 30 kilowatt range in air cooling, which is really that top end of how people deploy that. Being able to take this water cooling from that point up to 80 kilowatts per rack really provides an extension of anything else that's been available in that area previously, and even took us innovation even into the power system that comes in. We use high voltage AC directly into the racks so that we can get the most efficiency of how we provide that power in. Again, great offerings that complement each other.
Yeah, yeah. Well, John, this looks like a significant step forward in density and power and cooling for HP. What about headroom to grow? I mean, certainly Intel is not going to stand still. They're going to keep introducing new processors. Do you have the headroom for the power and the cooling for future generations?
Yeah, in terms of the way the systems are deployed, we absolutely have that capability to get what we know are going to be higher wattage processors inside those systems. The number of those that we get deployed, the GPUs themselves, we know continue to push those limits. The fact that we've set that bar at 80 kilowatts per rack, we know it's a pretty high bar compared to anyone else out there, and that is that capacity that we've put inside that system for headroom.
Yeah, yeah. And I guess kind of a wrap up here, John, there's a lot of accelerators being used in HPC these days. Does this system have a way to accommodate that?
Yeah, the picture you saw earlier where we have 2 servers inside that design, you could either have 2 separate servers or a 2-socket server that also supports 2 high wattage accelerators. And we'll be announcing those accelerator details both at International Supercomputer and other supercomputing shows here throughout the year.
Well, that's terrific. Well, John, I want to thank you for sharing this with us, and thanks again for coming on the show today.
Thank you for inviting me, and I enjoyed the time talking to you today.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.